Bismillahirrahmanirrahim. We proceed with our discussion on main memory management and discuss further more concepts in it. The next topic of discussion in this lecture, we will continue with fixed partitioning, as you can see in the outline, and discuss what are different placement algorithms related with the fixed partitioning. As already mentioned in previous lecture, that in this chapter we will be discussing primary memory management, mainly RAM, and next few chapters will be on secondary storage, especially virtual memory. So a process as a whole should be brought in RAM if it is not divided in functions or overlays. Overlays here means dividing a task in small manageable units, which we normally do with the help of functions. So if a program has different functions or different overlays, so every single function will be loaded independently, considering it an individual process. That means if a program has three functions, so three independent processes are created from it. Main memory is normally partitioned in two ways, either fixed partitioning or dynamic partitioning, while paging and segmentation is actually the partitioning of user programs, which we will be discussing in next lecture. What is fixed partitioning? If the RAM has been divided into collection of non-overlapping regions, the one shown in the image, so such partitioning is known as fixed partitioning, as once they are created, they get fixed and cannot be changed. You might have created partitions of your memory, so you would be having an idea what a partition is. If the RAM has been divided into chunks of regions which are permanent, so such partition is known as fixed partition. Fixed partition can be of two types, either equal or unequal size. If all the divided blocks are of same sizes, such partitioning will be known as equal sized fixed partitions. And if the blocks are of unequal sizes, so they are known as unequal sized fixed partitions. As you can see in the image, both the equal and unequal size partitions are visible. Whatever size of blocks are, once they are created, either equal or unequal, they are then fixed and cannot be rearranged or reorganized. In the figure, you can see equal blocks of 8 MB slots each, with 8 MB at the top being occupied by the kernel, and rest of the all equal size slots are available for the user tasks. While in the unequal sizes, you can see different blocks having different sizes of slots, and again kernel occupies some fixed space at the top of the RAM. If a process is small in size, then the partition, so it would occupy whole of the partition. For example, a process of size 2 MB would reside in complete 8 MB slot. How processes are placed in those partitions or slots? Any process whose size is less than or equal to a partition size would occupy that partition. If all the partitions are occupied and another process is required to be loaded, so first operating system has to make a space for it. And this can be done by swapping out one of the processes. And then the required process will be loaded in that free partition. But again, it may be possible that the size of a process may be higher than the size of all available slots, both in the equal and unequal size partitions. Then it is recommended that processes should be partitioned in small functions or chunks, so that every chunk is then treated as a process and space is then available for every small chunk as per their size. This is the reason structured programming came into existence, in which programs are given structure by splitting them in manageable units in order to be small enough to be loaded in RAM. With the use of fixed partitioning, the use of main memory is highly inefficient. And this is one of the drawbacks of fixed partitioning. Because any program, no matter how small it is, occupies the entire partition. For example, if size of program is 2 MB and it occupies 16 MB partition, so memory use becomes inefficient as 14 MBs goes waste. That means another fragment gets created within the partition, and this problem is mainly known as internal fragmentation. Why so? Because the process is not able to utilize whole of the 16 MBs and would only use 2 MBs, leaving remaining 14 MB space as waste. Neither it is using itself this 14 MB space, nor it is available to be used by any other process. This problem is very much evident in equal sized fixed partition, as all the partitions are of same sizes, and a process would waste same size of partition no matter in whatever partition you place it. But unequal fixed size partition lessens this issue. How? As only smallest available partition, which can accommodate the size of the process, will be utilized and less internal fragmentation will be created. For example, a 2 MB process, if placed in 16 MB partition, will waste more space as compared to 8 MB slot. But still the problem exists, though it gets lessons. IBM's operating system, multi-programming with fixed number of tasks, used equal-sized fixed partition, and they may not be present in today's latest operating systems. What is the placement strategy for a process to be placed in fixed partitions? There are two separate placement strategies for unequal size partitions. But for the equal size partitions, no strategy is required, as all the partitions are of equal sizes, so it does not matter where a process resides. If all the partitions are occupied, so space needs to be created for the new process by swapping out one process from RAM. Normally, the blocked processes are swapped out. For unequal size partitions, there are two placement strategies. One is the use of multiple queues. For every size of partition, a queue is made that holds processes equal to or less in size than the partition. So depending on the size of the process, if a partition for its size is not available, it has to wait in the respective size queue to get a chance to be loaded in that partition. This strategy helps in reducing internal fragmentation. But again, memory use goes inefficient, as some of the partitions may never get occupied due to non-availability of that sized processes. So their respective queues will remain empty. Hence, memory management is not properly done. If partitions are available that can accommodate a process in different queues, so instead of letting processes wait in queues, those available partitions can be utilized, but at the expense of internal fragmentation. Another placement strategy for unequal size partitions is the use of single queue. All the processes of different sizes will be stored in this single queue. An appropriate size partition will be selected for it before loading it into some partition. This strategy increases the level of multiprogramming as more processes will be loaded in memory, but again at the expense of more chances of internal fragmentation. Next topic of discussion, as mentioned in the outline, is dynamic partitioning, and we will see what are the placement algorithms with the dynamic partitioning. We have discussed fixed partitioning, and now is the time to discuss dynamic partitioning. In dynamic partitioning, the partitions are made on the basis of size of the process and is very flexible. That means partitions can be changed. Change in partition means the size of the partition can be changed anytime. In start, memory is empty strand and one by one partitions are created on the basis of the size of the processes. No matter how big or small a process is, exact sized partition will be created for it in the memory, until we reach to a point where very small spaces that are also known as Colson holes or simply holes are created all across the memory. These holes are tiny, so small that no process of this size may be present. So this problem is known as external fragmentation, as fragments inside partitions are again made. But external fragmentation brings a benefit or advantage, as those holes can be utilized by any other process. While in case of internal fragmentation, the free wastage space is not available to be utilized by any other process. So here in case of external fragmentation, operating system will apply a technique known as compaction. Compaction will collect all the holes and make a big partition that is large enough to hold a process. IBM's multi-programming with a variable number of task operating system implemented dynamic partitioning. You all will be implementing both fixed and dynamic partitioning practically. This is how dynamic partitionings are created. In figure A, you can see an empty strand of memory with kernel occupying some space while rest of the memory is available. And you can see no partitioning being done. In figure B, process 1 of size 32 KB occupies exact size in memory, and a partition is creating holding process 1. Process 2 arrives and occupies 224 KB space just below process 1, which is its exact size, and another partition gets created. Process 3 has 288 KB size, which makes another partition of exact its size right below process 2. A free hole of 64 KB is left, which is small enough to hold any process. Now process 4 is required to be loaded, whose size is 128 KB. But we do not have enough space in memory to load it. Now, if all the three processes in memory get blocked, that means they are now waiting for some device or event. So operating system can swap out one of them to make space for process 4. So in this case, for example, operating system swaps out process 2. After swapping out process 2, a free partition of 224 KB is now available, as you can see in figure E. So process 4 is brought in this free space. Process 4 has 128 KB size, so it will not occupy all the 224 KB partition. Rather, another partition of 128 KB created within this 224 KB partition. So you can see a hole of 96 KB formed in figure F. This 96 KB hole is small enough to hold any other process. Now, for example, process 2 is required to be brought in again, and there is no enough space available in memory. So operating system, for example, swaps out process 1, which is already blocked and not running currently, and a free partition of size of the process 1 is created, as you can see in figure G. Process 2, which is of size 224 KB, is loaded in that partition, as you can see in figure H. And another small hole of 96 KB is formed. You can see 3 small holes in figure H. All these small holes throughout memory actually waste memory. And this problem is known as external fragmentation, as these holes are external to any occupied space. So now operating system would apply a compaction technique which will collect all these holes and create a big partition of 256 KB, which is now big enough to be occupied by any process. Compaction, though, is a good technique, but it is expensive, as execution of all the processes go stop, since memory addresses of processes are now relocated. Processes are shuffled to move up in order to collect holes at the end of the memory. So memory addresses of all or some of the processes may be changed during compaction. That is all for now. We will continue our discussion on main memory management in next lecture. I thank you all.